thanks to Sandeep and Pratap, Rajdeep for arranging the whole thing. So I guess I'm giving 3 talks on symmetry protected topological faces, topological insulators beyond band theory. So my name is Senthil, now at MIT, but I did spend 2 years of my life in IISc some 10 years ago. So I was instructed by Rajdeep that I should try to make this first talk accessible to both theorists and experimentalists. So I hope I've tried, I certainly tried to do that, and I hope it's successful. So please keep asking me questions if something is not clear. Okay, so I've worked in this area for about 5 years now, and most of my work was done with this guy, Chong Wong, who's officially my PhD student till about a couple of years back. And it's fair to say that I learned a lot more from him than he did from me. So a number of other collaborators, some of whom you might know. So people at MIT, Andrew Porter, Adam Nahum, and Max Metlitsky. And Ashwin Vishwanath, you may know him. I don't know if he's been here recently. It's now at Harvard, and a bunch of other people. So some of these are condensed matter theorists, some of these are field theorists, and some of these are numerical people. So there's really all kinds of input that's come into this field. And I've not collaborated with math people, but there's a lot of interest from the math community as well. Okay. So topological insulators is a huge thing that happened in condensed matter physics about 10 years back. That's come to dominate many aspects of condensed matter, quantum condensed matter physics this last decade. So the big realization that happened about 10 years back was that within free electron band theory, that there's 2 distinct kinds of insulating faces in the presence of time reversal symmetry. There's the conventional band insulator, materials like silicon and so on. But there's a new kind of band insulator that whose existence became clear only 10 years back, known as the topological band insulator. And this topological band insulator occurs in materials where there's strong spin-orbit coupling. So it's doesn't occur in the simplest kinds of model systems that one might write down, say in Ashcroft-Mermin or other condensed matter textbooks. Right? You have to worry about this thing called spin-orbit coupling, which usually, at least when I was a PhD student or an undergrad, you dismissed as a complication not really worthy of the attention of people interested in general phenomena, general principles. Right? But this has come to play a huge role in enabling the possibility of this new kind of band insulator. So the usual characterization of a topological insulator is that even though it's insulating in the bulk, if you have an open surface, that at the surface there are conducting channels, it's a conductor at the surface, but it's an unusual conductor. And in 2 dimensions, in 2 space dimensions, there is the topological insulator is often called a quantum spin Hall insulator. The terminology doesn't matter. But what's interesting is that at the surface, at the one-dimensional edge of a 2-dimensional topological insulator, there are conducting electrons, and these mobile electrons, they have the property that the spin of the electron is tied to the direction in which it moves. If it moves in this direction, its spin, say, points up, and if it moves in the opposite direction, its spin points down. So there are conducting edge channels, but the spin of the electron in this edge channel is tied to the direction of propagation. Okay? And in 3 dimensions, the surface, an open surface, is 2-dimensional, and at this surface there is a metallic state where the dispersion of the electron obeys the Dirac equation, and more specifically there's a single, or more generally odd number of Dirac cones that characterize the surface dispersion of the dispersion of the metallic electrons at the surface of this insulator. So why is all this interesting? Right? That's the 0th order question. Maybe to condensed matter physicists, we say, oh, this is all so great, but Sandeep may wonder, why are these people excited, or Shiraz, right?
Just to ask, in the 2D case where you have 1D boundary, also it's a Dirac dispersion, that is, it's relativistic.
Right. So for 1D electrons, if you go near the Fermi points, it's always relativistic dispersion. So there's nothing very special about Dirac or non-Dirac, right? You don't see the bottom of the band, right? Because it's always linear. Right? So a metallic surface within band theory, we have a metallic surface that exists in a bulk insulator. That by itself is nothing unusual. Many solids have surface states which are metallic for whatever reasons due to details of the band structure. But there's something amazing about the surface, just as a phenomenon that a metal can show. In general, if you take a metal and you disorder it, put in impurities, they'll tend to localize the electrons. Right? So electrons can't move very efficiently in the presence of random impurities, and eventually, if the impurity concentration is big enough, you can convert a metal into an insulator. Right? Now, an amazing property of the surface of this topological insulator is that you can put in any amount of dirt that you want into the surface, and the surface will stay metallic so long as you preserve time reversal invariance. Right? So that's something that ordinary metals do not do. Right? You can always kill a metal and make it an insulator by making the metal dirty. But you can't do that at the surface of this topological insulator so long as you preserve the symmetries.
So it just remains a metal.
It just remains metal. That's right.
Resistivity can increase.
Absolutely. That's right. It will never become a true insulator, at least within the band theory approximation. Okay. So from a
And I'm really sorry to ask this. What exactly is a metal? I mean, do you mean it's
right.
by Landau's?
No. A metal is something that conducts electricity.
Just conducts it.
Exactly. That we'll use the high school definition of a metal. Okay. In fact, that's it's a great question to ask. Many times in condensed matter physics, we forget that that's the best definition of a metal, but it indeed is the best. Anything else is much more specific and, okay. Now, the other feature of this story, yeah. Just call me Senthil.
You're saying that even if, let's say, the resistance is very high,
Yeah.
and even in that case, if you say that it's basically metallic, so are you saying that the resistance versus temperature dependence
No.
is?
So I'm only saying the resistance at zero temperature, resistivity at zero temperature is some constant. It's not infinity. Right? So there's diffusion at zero temperature. Yeah, no, that's right. Yeah, those are non-universal things. Right, so if I have a d-dimensional solid, then the surface theory that one gets for the surface of this topological insulator is in some sense impossible in a strictly d-1 dimensional solid with the same symmetries. Okay? So this kind of statement is something that we'll talk a lot about in these lectures. But within this band theory approximation, an example of this phenomenon is what happens, for instance, in this 3D topological insulator. The surface realizes a two-dimensional Dirac electron, and this, in the simplest case, there's just a single Dirac fermion, and a single massless Dirac fermion, Dirac cone, is not an allowed band structure of any 2D time reversal symmetric metal, and that is known for many years. There's even a theorem in the context of lattice gauge theory that you can't lattice regularize a single Dirac fermion while preserving time reversal, blah, blah, blah. So this state nevertheless exists quite naturally at the surface of this three-dimensional topological insulator. And indeed, it's been seen to exist in experiments and so on, and the theory is in great shape. Okay. So one of the great things about the story of the topological insulator is that, I'm a theoretical physicist, and I think this is a story that gives tremendous joy to all theoretical physicists. There's really a triumph of theoretical physics. Right? It was led by theory, the possibility that such a thing might exist first came out of theory and fairly abstract considerations. Guess the pioneer in this is Charlie Kane. A lot of the original contributions came from Charlie Kane and his group. But very soon after, there was prediction of materials by Shucheng Zhang and his gang, and by Liang Fu and Charlie Kane. And experiments came later, and it more basically confirmed the story. Right? So it's really the triumph for theoretical physics. So I'm very glad. So, usually, I don't know about other fields of physics, but in condensed matter physics, we dream up all kinds of things if you're a theorist. And if something remotely similar to what you've dreamed up shows up in an experiment, you're very happy. Here, exactly what people dreamed up showed up in experiments. Right? So it's great. I think we should all theorists should celebrate this kind of thing. It's a rare event when it happens, so one should cherish it.
Happens all the time in string theory.
Yeah, I know. All right. So what kinds of materials, right? So in 3 dimensions, so 3 dimensions is the really interesting case where the phenomena are most novel. In 3 dimensions, this topological band insulator requires spin-orbit coupling. And so in the presence of spin-orbit coupling, there's no conservation of spin angular momentum anymore. Right? Spin is locked with the orbital angular momentum. But remember, we are dealing with a crystalline solid where there's no spatial rotation symmetry. So spatial orbital angular momentum is not conserved by itself anyway. So in the presence of spin-orbit coupling, there's no conservation of any component of either spin or orbital angular momentum. Right? So spin conservation is just gone. Right? But of course, electric charge is still conserved, and there's time reversal symmetry. So those are the important symmetries that protect the topological insulator. And the early materials that Fu and Kane discussed, and the experimentalists, were weakly correlated materials, things like various alloys of bismuth, bismuth selenide, bismuth telluride. There's about 100 materials now that are known to be in topological insulating phases. Maybe the number is even bigger. It was 100 the last time I looked, a couple of years back. So there's many, many materials that we now realize are topological insulators. And some of these are materials that people had been studying for a long, long time. They're useful in various applications and so on, but without ever recognizing that they were doing all these cool things. Right? So there's some interesting candidates beyond this early generation of materials that people are now talking about. So one of them is actually a very famous material in solid-state physics. It's called samarium hexaboride. There are probably people right here in TFR who've studied samarium hexaboride.
Samarium boron 6 is a controversy now. It's probably no longer at the quantum state. It's a strange metal.
Yeah, I know. I know. I was going to say exactly what you said just now, because this also is one of my other obsessions. And, if I'd not been asked to talk about SPT, I might have given an entire lecture on samarium hexaboride. And I have a theory of what's going on in samarium hexaboride. But that's not.
Yeah, I just want to tell you that yesterday we tried to search for superconductivity in SMT6.
Uh-huh.
Down to 100 microcurie, it is not superconducting.
It's not superconducting. Very good. I think we should chat about that. I think there may be a chance that it may become, we should chat about it separately. I've certainly thought hard about the latest story in samarium. This is a really interesting material. So that's why there's a name candidate in here. It's a candidate topological insulator. We'll see how ultimately the dust settles.
A few slides back you said that the spin always points in the direction of the momentum.
In the two-dimensional case, yeah.
So, and why is the chiral symmetry broken in this case?
Chiral symmetry?
The symmetry, whatever the symmetry is, why can't it point the other way as well?
Oh, actually, even in 3 dimensions, this is true. It's in the Dirac equation, right? So, the Dirac Hamiltonian is sigma dot p, right? So the energy eigenstates have momentum locked to the direction of spin. So So that's all there is to it from the formal point of view. So this is an interesting story. It's certainly a candidate topological insulator, but the dust may finally settle in the direction of something even more exotic than a topological insulator, right? So that is yet to be determined. There's many other rare earth alloys that people have proposed. There are various iridium oxides and so on. There's a big difference between this class of materials and this class of materials. So in this new class of materials, the active electrons that are probably participating in what makes it into a topological insulator are electrons from atomic d or f orbitals. And the electrons from those kinds of orbitals typically have strong electron-electron interactions, right? So they are tight orbitals. So the Coulomb interaction is enhanced if you have electrons from d or f orbitals as compared to s or p bands, right? So for these class of materials, band theory was a fantastic approximation and very useful as a way to predict exactly what the material will do. Now for this class, band theory is not that useful directly, and so you have to come up with some other way of thinking about the physical system. Okay?
But it's still the case, even though band theory is not a good approximation, that the edge states are more or less free.
We don't know. So sorry, these are all candidate states. So we don't know exactly what they will do, but they have been discussed as possible topological insulators, and we'll see what happens, right? But people are certainly talking about things like this, which then raises, the theoretical question of how should we think about this phenomenon beyond band theory, right? So that's the context from a materials point of view. That's the reason to think about this question. Okay. So how does the physics change of the topological insulator once electron-electron interactions are included? Okay? And this is important right now, both because people are searching for topological insulation in correlated materials, okay? And from a conceptual point of view, you obviously want to know what happens once you include interactions, right? It's how can you not address that question? And it's a foundational question, right? It's basic to the theory. Free electrons is, if you say it's protected just by symmetry, then it should be robust to having, nonlinear interaction terms. So is that statement really true, or is it not true? Okay. So I just made up a list of very basic conceptual questions that you can ask about this story of topological insulators beyond band theory. That is the first question that anybody would want to ask once you start confronting this issue of what happens beyond band theory. First, whether this phenomenon of a topological band insulator is destroyed once you have any interactions between the electrons, right? If this were true, then we have no business talking about topological insulators in correlated materials like samarium hexaboride or the iridium oxides, whatever, right? And as a matter of principle, we also have no business talking about it even in bismuth selenide, because even in bismuth selenide, the electrons after all do interact with each other, right? It may be okay to treat those interactions in some crude approximation where you pretend that they are free fermions, but conceptually it's wrong, right? So we had better address this question. But then you can ask whether there are new phases that have no counterpart in band theory. Where band theory is simply incapable of describing these phases. And what are their physical properties and which materials might these show up in? Okay? So all this means that we need to think about this phenomenon of topological insulation without the crutch of free fermion band theory. Okay? So even though the original discussion was based entirely in terms of thinking about band structures and invariance of band structures, topological invariance of band structures, in the modern context, we have to abandon that foundation and go to a different foundation. Yeah?
Elaborate a little. When you said band theory is incapable of this type, what did you, are you going to talk about it?
I am going to talk about it. The question is, band theory is an approximation, right? maybe that approximation fails to capture some phenomenon. Right? Yeah. Okay, so the question that you can ask related to these is, given that the original discussion of topological installation was by asking whether some band structure has some topological invariant, right? What should we even mean by the notion of a topological insulator beyond band theory, right? So we need to even define the concept of a topological insulator differently to be able to pose the question of what happens in the presence of interactions, right? So how should we generalize it to interacting electrons? So let's start by observing some features of the topological band insulator that are there within band theory, and then we'll use these features to define the state even without the crutch of band theory. Right? So first we know the bulk of the system has an excitation gap. Everything in the bulk is gapped. The surface is gapless, but the bulk is gapped. And the elementary excitations in the bulk are the same as ordinary electrons, or ordinary insulators. Right? They're just electrons. It's, one should contrast this with something like a fractional quantum Hall effect, where in the bulk you have all kinds of weird excitations, fractional charge, fractional statistics, and so on. Here is nothing there in the bulk. It's just electrons. Right? There's no weird stuff going on in the bulk. And despite all these seemingly trivial bulk properties, the surface is non-trivial. Okay. All right. So as a minimal generalization of this concept of topological insulator to interacting electrons, and let me phrase it in the context of strongly correlated insulators with strong spin-orbit coupling between the electrons, which is the original context in which topological insulators showed up. So we'll demand that whatever state we have has a bulk gap. So there's nothing gapless in the bulk. We'll also demand that it has no exotic bulk excitations, that all the excitations in the bulk are electrons or composites of electrons, and so on. So there's no fractional charge or no unusual statistics, nothing. But we'll allow for the possibility that there's no trivial surface states. Okay? So we'll just take these three properties as our definition of what a topological insulator is, right? And ask whether there are states of, are there such states of matter that exist in 3 dimensions with some symmetry? How many such states are there? What are their physical properties? Blah, 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 right? So there is a very interesting precursor of this. So once we've defined it this way, right, says a bulk gap, no exotic bulk excitations, but has no trivial surface states, you realize that immediately that there's a precursor to this in the context of quantum magnetism. Okay, so let me briefly mention this. This is actually a very famous precursor. So in the context of quantum magnetism, so what we are talking about are systems which or insulators with local magnetic moments which interact with each other through some spin Hamiltonian, right? And we'll demand that we have a paramagnetic ground state, meaning the spins do not order and break any symmetry. They preserve all the symmetries of the microscopic spin Hamiltonian. And this paramagnetic ground state will demand that it's such that it has a bulk gap, so it's nothing in the bulk, and that there's no exotic excitations in the bulk, no fractional spin, no fractional statistics excitations, but nevertheless might have non-trivial surface states. Right? So this is the spin analog of a topological insulator, right? And we'll call this a topological paramagnet in analogy with the terminology topological insulator. Okay? Yeah.
In this case, do you care to qualify, because you're sort of defining a new way of defining what do you mean by non-trivial, not the standard surface states that would come even in a band insulator like silicon. You want to discount those.
Right. That's right. So we want these to be symmetry protected, meaning so long as you protect the symmetries that define the system, that the surface cannot be trivialized in some way. Right? It can never be a totally dumb trivial state.
I mean, one thing could just be that there is a degeneracy tied to the surface state.
There could be that's right, yeah.
At least, I don't know, in the Haldane spin chain
Right, that's what I'm going to talk about next, yeah. More generally, I mean, degeneracy could be subtle, right? It could be, in higher dimensions, it could be more complicated things. But so there's a very old example of this phenomenon, which is this antiferromagnetic spin chain of spin 1 moments in 1D, so-called Haldane chain. It's actually very topical now. I think everybody knows this because Haldane got the Nobel Prize this year, partly for this work, right? So at least in the news media, you've heard about this thing. So the model is just spin 1s on a 1D chain, 1D lattice with this interaction with J positive. So that's the antiferromagnetic spin chain. And what Haldane argued in 1983 was that this spin chain has a unique ground state on a, let's say you put it on a ring. So I have periodic boundary conditions in this one dimension with periodic boundary conditions. It's on a ring. And on a ring, it has a unique ground state and has a gap to all excitations. Right? And in 1D, there's no real possibility of having exotic statistics or exotic anything else. So the gapped excitations of spin 1 objects, you can think of them as gapped magnons. So this model, this Haldane chain was a bit later argued to show this amazing phenomenon that even though it's seemingly almost trivial in the bulk, that if you cut it open and have it as an open spin chain, then at the boundary there's dangling spin half degrees of freedom, right? Which is a spectacular phenomenon. You're starting with what microscopically are spin 1 degrees of freedom, but then you cut it open and you see that there's some life at the edge, and what's at the edge is half of what's there in the bulk. Right? It's a spin half degree of freedom. Right? And these edge states are protected by the symmetry, by some of the symmetries of this Hamiltonian. For instance, it could just be time reversal symmetry, or it could be spin rotation, spin SO3 symmetry. So there's many symmetries that are that can protect these edge states as non-trivial objects. Either spin rotation or time reversal, or of course if you have both, that's good enough, or lattice inversion, the parity transformation. All of these are protecting symmetries. Right? So this is an example, perhaps the earliest example in history of a symmetry protected topological paramagnet. So of course it goes, it's several decades prior to the topological insulator itself, but it's only recently, post-topological, many years after topological insulators arrived on the scene, that we realized that the Haldane chain and this topological insulators are really the same kind of phenomenon. Okay? So let me explain this physics of this Haldane chain a little bit more, not in too much detail, but just a bit more. You had a question?
No. I think I'll wait till you.
Yeah, okay.
I just wanted to ask you what exactly means that it's protected by the symmetry, but probably...
Right, so let me answer that now. Right? So for instance, if I break time reversal, then I can turn on a magnetic field that couples to the Zeeman coupling to these spins, and then the twofold degeneracy of these spin half moments at the edge is lifted completely, and so I'll just polarize the spin half degree of freedom. Right? Now as I keep increasing the field, nothing will happen. It's just this edge spin is just pointing along the field. Right? So there's nothing non-trivial about that edge spin anymore once I break the symmetry. Once I break, in this case, time reversal, spin rotation, everything. Right? So it's in that sense that it's the non-triviality of the edge states of the edge spin is protected by symmetry. Okay? Yeah?
Does the symmetry always have to be non-unitary, or can it be unitary as well?
Yeah, so spin rotation is a unitary symmetry, right? So it can be unitary. And even in the standard topological insulator, it's not just time reversal. We usually say it's time reversal. And from a practical point of view, that's correct. Because if you're an experimentalist, that's the symmetry you most likely might break with a magnetic field. But what really protects it is charge conservation and time reversal. Now, if you're an experimentalist, it's not natural for you to try to break that charge conservation. You have to bring a superconductor close to it, blah, blah, blah. So it requires work, right? So the real symmetries that protect it are a unitary symmetry, which is charge U1, and time reversal, which is anti-unitary. And in this example, likewise, it could be protected by time reversal, which is anti-unitary, or spin SO3, which is unitary. Right? Is that good? Yeah. Okay. So I'm going to give a very cartoon level description of this Haldane chain. So the basic idea is that each spin, which is spin 1 in the bulk of the chain, one way to think about what the ground state is doing, which enables you to understand why there's this dangling spin half moment, is to think of each spin 1 as a combination of 2 spin halves, right? And now imagine that each spin half has formed a singlet with a partner spin half to either the right or to the left of this site, right? So then if you have the system in a periodic chain, every spin 1 is taken care of because it's formed a bond with a spin half member of that spin 1 has formed a singlet bond with a partner, and so everything is rigidly locked. But if you cut open the spin chain, then you expose a dangling, so let's say you cut it open here, and then the 2 spin halves that made up the spin 1, one of them has formed a singlet bond here, and everyone else has formed a singlet bond, but this other partner is left without anybody to bond with. So it's left dangling. Right? So that's the origin of this dangling spin half edge moment.
So the state that you've drawn there is an approximation to the true ground state?
Right. So the state that I've drawn here as it stands is an approximation to the true ground state. Now, first of all, the state that I've drawn here doesn't even live in the correct Hilbert space, because the correct Hilbert space only has spin 1s at each site, while here I have 2 spin halves, which means in principle I have both spin 1 and spin 0, right? But then I could imagine projecting the state to the right Hilbert space and then ask whether that's a good wave function for the system. It turns out it's not an exact ground state wave function for the original Haldane chain, but it's the exact ground state wave function for a modification of the Haldane chain that Affleck and company introduced in 1987. That's the same as this model, but with an extra term which involves the square of this operator with the coefficient 1 over 3. And then it's exactly soluble, and this is the ground state. Okay? So it's a nice analogy to explain the physics of this Haldane chain through a cartoon picture. I actually drew this cartoon picture 3 years back in trying to give some colloquium talk on this kind of story. I was, when the Nobel Prize announcement came out, I was amazed to see that someone in the Nobel Committee had the same analogy in mind, and their popular explanation had a similar picture. Right? So the picture to think about is a group of children arranged in a line that are holding hands very tightly with each other, and the Hilbert space of these children that we'll focus on is not the children themselves, but on their clasped hands. Right? So in the middle, these children hold hands very tightly, and anywhere you look in the middle, you only see a pair of clasped hands. But if you cut open this chain, not by cutting a child, but by imagine you have an open end of the chain, then one child has a free dangling hand, right? So it's the same, the quantum version of this story is what's giving you this physics of this Haldane chain.
And to make that state, you first make the state in the larger Hilbert space and then project.
Exactly. Exactly. That's right. Okay. So that's what I'm going to say about the Haldane chain so far right now.
So these arguments only can be extended to 2D?
Not directly, but there's a version of this kind of construction that works in any dimension. Right? That's part of the recent progress.
So if this was a 2D antiparabolic Heisenberg chain, would I still have surface states at elementary level?
Right. So not for the standard Heisenberg Hamiltonian. For the standard Heisenberg Hamiltonian, we know that it just on a square lattice just orders magnetically. Right? But if you add enough weird interactions, depending on what symmetry you have, you could get a paramagnet first, and then you could get a topological paramagnet. Right? So there are Hamiltonians that you can write down that will do 2D and 3D analogs of this phenomenon with appropriate symmetries. It's harder to write down in higher dimensions exactly soluble Hamiltonians with full SO3 spin rotation symmetry that go into these phases, but let's say just an Ising symmetry you can write down.
And sorry, Senthil, this is something you'll probably talk about, but just from a more abstract point of view, is the fact that the edge states are in a projective, not in a true representation of SO3, in a sense, the key?
That is the key in this 1D example.
Okay.
That's right.
So somehow here the edge protection you could see in a clear way if you turn on a magnetic field.
That's right, yeah.
There's a sort of deeper, that you have an underlying theory with some symmetries, and then somehow you get edge states which
transform projectively, even though in the bulk everything transforms linearly. That in 1D, that's the entire story of these SPT phases. In fact, that's the way to classify this bosonic SPT phase in one dimension. Just classify projective representations of the symmetry group.
And that guarantees all the properties you
Exactly. That's right. Yeah. Right. Okay. So what we now see is that there's two kinds of phases which are very similar to each other. Right. There's the Haldane spin chain, and there's the topological band insulator. Right. So once you see two examples, you expect that there's many, many more of the same kind. And indeed, we now know that there's really a vast universe of phases which are of the same kind, which exist with interactions, without interactions, and there's a big story. Right? So this has been going on for a while. I'll give various references as we go along. But the most serious attempt to classify all such phases of matter, the most serious first attempt to classify all such phases of matter was made by Xie Chen, Zhengcheng Gu, and Zhengqing Liu and Shougang Wen a few years back with some very formidable mathematical methods. It's an effort that existed before them, perhaps less complete. This is not complete either, and it's an effort that's continued to the present day with more and more sophisticated mathematical methodologies. I won't talk about this formal classification at all in my lectures. I'll keep the focus more on the physics end rather than on the formal math end. All right. So one should contrast wait, I think I'm missing a slide. Yeah. Let's see. Maybe missing a slide. So let's contrast this structure of the symmetry protected topological phases with other interesting phenomena in modern condensed matter physics. So one of the most amazing things that I learned about in condensed matter physics was this possibility of the emergence of exotic quasiparticles with fractional charge or fractional statistics in a condensed matter system. That's what drew me into condensed matter physics in the first place, right here in TFR as a VSRP student in not that long ago. So this happens, for instance, in the fractional quantum Hall effect. Now, there's something else that's even more exotic than the presence of exotic quasiparticles that many of us have spent a long time working on. These are phases of matter in which there may be no quasiparticles at all to describe the excitation spectrum. So the notion of a quasiparticle fails completely. And that is perhaps what's going on in all these non-Fermi liquid metals that routinely show up in experiments. There's no theory of, say, the strange metal in the high TC superconductors. In case like these, the notion of a quasiparticle presumably fails, and we have no idea really what to do. What other framework should be used to replace that that structure. So these SPT phases, in contrast to these amazing phenomena, are things in which we explicitly say all the amazing things that we know condensed matter systems can do, we'll forbid, right? So we try to squeeze the life out of a phase and see whether it still has some room to move. Can it do anything interesting if we don't allow it to do all the interesting things that we knew condensed matter could do, right? So that's the game that we are playing, right? So why should we bother to play this game, right? So the first reason is that these phases might exist, right? There, people are searching for topological phenomena in samarium hexaboride or iridium, yttrium iridium oxide or whatever it is, then we'd better understand what the possibilities are. And so then it makes sense to think about electronic solids with the same symmetries as a topological band insulator, see what might happen, blah, blah, blah. But there's another reason to study these phases, which is more theoretical, which is that it's perhaps the simplest context where three of the main themes of modern quantum condensed matter theory intersect, symmetry, topology, and strong interactions. And there's huge payoffs to studying this interplay in the simplest possible context. Right? It turns out that we've gotten enormous insights into more complex systems which do precisely the kinds of weird and interesting things that we were originally interested in. We've learned a lot more about fractional charge and fractional statistics, using the insights from SPT phases than we had for many years before that, right? We're also learning quite a bit about these phases with no quasiparticles, non-Fermi liquid phases and things called quantum spin liquids and so on, which are much more exotic than SPT phases, but understanding the physics of SPT has enabled us to understand a lot more about these phases. And there's many interesting connections to developments in the field theory literature. Yes, Shiraz, there's a surprising connection to Shiraz's past that, and Sandeep's, and probably many other field theorists in the room. I actually don't know who the field theorists in the room are, but other than maybe three of you. And to the math literature, and there are mathematicians working in this area right now. Okay? Now, related to all this, there's a final reason why I personally have been very excited about these phases. It turns out that they are centrally connected to all kinds of other frontiers of modern condensed matter physics, not to mention field theory and math. I'm very parochial. My interests are purely in condensed matter physics, right? So I'm interested only if it buys me something in condensed matter physics. The spin-offs for field theory and math are nice, but I'm not, deeply motivated by them, only mildly motivated by them. Sorry? What a shame. Yeah, that's the way life is. So the symmetry-protected topological insulators, there's several other topics in modern condensed matter physics that just a couple of years back, we as well as Ashwin and Max Metlitsky recognized or connected to all these other problems. So quantum spin liquids is something that I've already mentioned. It's a big topic in quantum magnetism. Lots of theoretical work, lots of experimental work, very hard theoretical questions. And it turns out there's a very deep and close connection between these two topics. And a surprising connection is to the physics of the two-dimensional quantum Hall effect and what's known as composite fermions in the two-dimensional quantum Hall effect. Again, a very flourishing topic in the 1990s, although there were some leftover questions, and following a beautiful insight of Damson, it's now become clear that this is all integrated into the study of three-dimensional topological insulators, right? And these connections are really weird. We can study phenomena in three-dimensional quantum spin liquids, in the context of theories that were originally developed to describe, materials like ytterbium, titanium oxide, or praseodymium, zirconium oxide, and so on. Three-dimensional pyrochlore lattice materials with electron magnetic moments, and see in those theories precise analogs of phenomena in the 2D quantum Hall effect. Right? So that's amazing. Right? Things that earlier we had no way to connect, no reason at all to suspect we're connected. Now we see that they are intimately connected with each other. Right? And likewise, there's a different set of phenomena in 2 dimensions associated with quantum phase transitions that are beyond the standard Landau, Ginzburg, Wilson description. It's things that I myself spent many years working on. But now, again, this too has gotten integrated with the study of symmetry protected topological insulators. So in these lectures, given all these reasons to study SPT, I'm just going to focus on the physics of SPT phases. I said time permitting, but I think there will be no time for me to do any of these other things. And Mohan is not here, but I already apologized to him. He cursed me because he claimed I put this in the abstract of my talks. I'm going to emphasize the physics rather than the math, right? Partly because I don't really know the math. All right. Okay. So let's go back to these basic questions about SPT phases. So free fermion phases, stable independence of interactions, or they're new phases that have no non-interacting counterpart. So let's start with the first question. Now, over the years, we've come to recognize that some free fermion SPTs are actually unstable to interactions. Right after the original conception of a topological insulator, there was a formidable mathematical classification of all kinds of free fermion, gap free fermion Hamiltonians by Kitaev and by Shinsei Ryu and Andreas Ludwig. And shortly after that, Fritkowski and Kitaev realized that that classification is not robust to interactions. So this is an alarm bell, right? One should worry. Okay, it's really an artifact of free fermions. And by now we know examples in many dimensions of this kind of phenomenon. But something that's stable in the free fermion approximation, stable meaning it's distinct from a trivial insulator in the free fermion approximation, is no longer distinct once you have interactions. Okay?
Sorry, does that mean, for example, that the degeneracy on the edges goes away?
If you have strong interactions, that's right.
So, but is there a kind of a region in interaction space for which it exists and then disappears, or does it disappear immediately?
Oh, typically there will be a region in which it's stable, but it's a question of absolute stability, right? So a statement we usually make is that surface state is protected so long as this symmetry is preserved, no matter how strong anything else that you do to the system is. Right? But if you can add strong interactions, for instance, I said that the surface of the standard topological insulator is always metallic, however strong the disorder is. You could ask, is it always metallic, however strong the interactions are? The answer is that it could be an insulator if you make the interactions very strong. Right?
What happens on the other side? See, you say strong spin-out coupling you need for this protected state.
Right.
So can you theoretically weaken this spin-orbit coupling and see where will it take it? At some point, this protected state will go. Can it be seen theoretically?
No, so that really, yeah. So what needs to happen within this, so the question you're asking is a question for within band theory. Right? So within band theory, as you weaken the spin orbit coupling, you can ask whether you can get rid of the surface state. To get rid of the surface state, you have to have a bulk phase transition. So you have to close the bulk gap. So you have to pass through a metallic state in the bulk. So that you'll see that very easily. Right? Your bulk insulator is no longer an insulator, you'll know.
I didn't understand the answer. So you mean that a very weak spin orbit coupling will also imply a topological surface state?
No. So the focus on spin orbit coupling is because that's what enables this phase to exist.
Yeah.
Right? But conceptually, the most important thing is what the symmetry is. Right? There's charge conservation and time reversal and no conservation of spin. So spin orbit coupling removes spin conservation, right, and leaves behind just these symmetries which can then protect non-trivial surface states.
Your starting point is these assumptions, not how spin orbit coupling is.
Right, that's right, yeah.
Why is it important that spin is conserved?
Oh, if you have spin conservation, then there's additional symmetries, and then you have to ask whether the state can exist in the presence of these additional symmetries, right? And within band theory, it cannot. Okay, so I'll give you a way of thinking of understanding that result from a totally different point of view as we go along, right? Non-perturbative point of view.
Sorry, Senthil, you should go on, but this seems like a very strong criteria, because usually I would have thought if near the free fermion
Right.
theory, in some vicinity of that,
Right.
the phase is stable.
Right.
That's good enough. I mean, what happens arbitrarily far away? I mean, hell can break this. To demand even that the phase continues to exist as long as time reversal, etc., is preserved, very far away. That's a very strong.
I know, but in this business, we are very ambitious, right? Because these phases are so simple that we think we should be able to answer all matter of principle questions. So the question we're asking is a matter of principle thing, right? Is symmetry alone enough to protect the distinction of the state from a totally trivial band insulator, right? Or do you also require that it be weakly interacting? Do you have to say there's this symmetry and weak interactions? Or you just say this symmetry and any strength of interactions, disorder, anything else, right? So that's the question we're asking, right? Exactly what is required to protect the state, right?
Sorry, just to go back to the Haldane spin chain, as long as the bulk was what it was, I can see why the dangling bonds can't be upset
Right.
and so on.
Right.
But now if I allow arbitrarily strong interactions
Right.
in the bulk, you might think you just rearrange everything and
Right, but so long as there's no phase transition in the bulk, these edge states are protected, right? So that's
So that's sort of what I was getting at. So in these cases, do you mean you turn on interactions, but unless you hit some analog of a phase transition?
exactly, that's right.
So that's the
So long as you don't have a phase transition, right? In a bulk phase transition, that's right. Yeah, that's right. Right. Okay. So these results may be worrisome, but if you're a practical person, these examples are examples not of topological insulators, but they're of topological superconductors. And if you're a practical person, topological superconductors haven't really been realized in experiments. So you say, okay, maybe we worry about this at some later stage, right? We really just want to worry about the thing that we already have, which is a topological insulator, right? So are the usual topological insulators stable to interactions, right? So let's ask that question, and the answer is yes. I'll illustrate this in the next few slides, with a line of reasoning that is extremely powerful and will lead me to the kind of thing that I want to talk about in the next lectures. So let's start with some very, very obvious statements, right? We are talking about an insulator with no exotic elementary excitations, right? An insulator made out of objects that the underlying objects are all electrons. So all excitations must carry integer charge, right? Because no fractional charge by definition. And if n is odd, I'm putting together an odd number of electrons, so this must be a fermion. If n is even, I'm putting together an even number of electrons, so it must be a boson. Okay? Now, I'm going to use as a probe of this material an object. I'm going to imagine a probe experiment that no experimentalist, however talented, can do, right? But we are theorists, right? I am a theorist. Some of us are theorists. So we are allowed to dream up any probe that we want of a material, right? Doesn't matter that it's not a practical experiment, right? And it turns out that the probe is to introduce into this insulator a magnetic monopole. Okay? And let's ask how this medium responds to the presence of a magnetic monopole. Okay? So obviously, even you guys will not be able to do this experiment. At least not right now. Right? But let's think about it anyway. And it turns out that this is a way to non-perturbatively constrain the physics of the material. Okay? And a reminder, an elementary magnetic monopole is the source of Hc over E magnetic flux, not Hc over 2E, it's Hc over E. Right? Okay. So let's understand how, the role of symmetries. Right? Now, under time reversal, magnetic fields are odd where electric fields are even, right? Which means that magnetic charge is odd and electric charge is even. Okay? Now, suppose the magnetic monopole has picked up some electric charge Q. Right? So I introduce the monopole into the medium and I ask, go and measure the electric charge near the monopole. Right? And maybe it has some electric charge, and maybe the charge is some number Q. So then I think about the time reverse version of the monopole that has the opposite magnetic charge, but since electric charge is even, the electric charge does not change. So the time reverse version also has electric charge Q but carries opposite magnetic charge. Now I should emphasize that the magnetic monopole is not a physical excitation of the system. Right? If I just solve the Hamiltonian and look at the excitation spectrum, I'll never find a magnetic monopole. I'm changing the system by introducing this magnetic monopole. Okay? It's an external probe object. Okay? So it's not bound by the same rules as internal dynamical excitations are bound by. So now let's ask about the following thing. Suppose I bring this monopole and its time reverse partner together and annihilate one against the other, right? Then what's left? Okay? Now what's left no longer has any magnetic charge, right? Because the monopole and its time reverse partner have opposite magnetic charges. So what's left has no magnetic charge whatsoever, right? So what's left must be a legitimate excitation of the system. Okay? Which means that Q itself, we don't know anything about Q a priori, but this combination of M and Tm, it has electric charge 2Q, and 2Q, because it's a legitimate excitation in the system, it must have integer charge. Right? So 2Q must be N times E, with N being an integer. Yeah? Right. So the reason the monopole is not an excitation is because it carried this magnetic charge. Right? So now I've gotten rid of it. Right? There's no more magnetic charge left in the system. Right?
But you still did something to the material and moved things around it by hand, right? So why should you expect it to dilate the original Hamiltonian?
It's an allowed state in the system. Right? There must be a state in the system with these quantum numbers. Right? It's not, there's no statement being made about this being an energy eigenstate. It's just that it's a state in the Hilbert space of the system. Whether it's an energy eigenstate or not depends on the particular Hamiltonian, which I don't want to talk about. Right? I want to make some statement that's true for all Hamiltonians. Okay?
When you say excitation, that does not mean energy eigenstate.
No. What I simply mean is that it's a legitimate state that exists in the system. Right? Now, given a particular Hamiltonian, you can always do something, evolve it after I annihilate these two things together. I can do some other time evolution with some external Hamiltonian, make it into an energy eigenstate. But that's not really the issue here. Right? So this equation strongly, completely constrains, almost completely constrains the non-trivial values of the charge that the monopole can pick up. So it really has only two distinct solutions. Right? So one class of solutions is that Q itself is 0, E, 2E, and so on. Right? In which case, all that's happened is that where the monopole was sitting, accidentally an electron also happened to be sitting there. Right? Now, and 0 and E and 2E are not really distinct from each other. You could have added any number of electrons, just dump them where this monopole was sitting. But there's another class of solutions to this equation, which is Q is E over 2, 3E over 2, and so on. And again, E over 2 and 3E over 2 are not really that distinct from each other. You could just have had an additional electron accidentally be sitting where the monopole was sitting. But this class of solutions is totally distinct from this class of solutions. Okay? So the fundamental distinction is between whether Q is an integer or Q is an integer plus half. Right? So we see that there's two distinct possible responses of this medium to an external magnetic monopole. And the only assumptions here are that it's an electrical insulator. And to talk about an electrical insulator, you need to have charge conservation. Right? Otherwise, there's no meaning to it being an insulator. And a superconductor is a superconductor. Right? So we have assumed charge U1. And by assuming that Tm, the time reverse partner, has the same electric charge as the monopole, we've assumed that there's time reversal invariance. Right?
Sorry, where did you even assume it's an insulator? I can imagine a superconductor you can't put in this flux, but where did you...
Where they assume that it's on a superconductor, strictly speaking, this notion of well-defined electric charge doesn't exist.
So that
right? So the charge, characterizing the state in terms of how much charge the monopole picks up is not a well-defined notion in a superconductor.
But the argument have worked in a normal conductor, which was not an insulator, just to ask?
Oh, in a conductor, the conductor, there's, it's always delicate in a gapless system to sharply define quantum numbers, right?
So you wanted a gap?
I wanted a gap system, right? That's just a dielectric medium, right? Okay. So it turns out that these two possibilities correspond precisely to the trivial insulator and the topological insulator. Okay? Yeah.
So wait, so this magnetic monopole is completely external, right?
That's right.
So it will have, you can talk about a charge in terms of the charge of the electron.
That's right. Yeah. The electromagnetic charge. Yeah.
Yeah, but what if basically the state of a material is such that the excitations have charge not E but some reason on the star, and then you have
No. In an insulator, so that's why I started with these trivial observations, right? So by assumption, there's no fractional charge, right? And charge is quantized, right? In an insulator, charge is quantized, right? Because charge, it's an incompressible state. Any insulator is incompressible, so charge is a sharply defined object, right? So you could have fractional charge, like in the fractional quantum Hall effect, right? It's still quantized, it's sharp, but it's fractional. But we prohibited that, right? So we only allow integer charge.
So naive question. Why
Yeah.
is the monopole central to this argument? In the sense that you had this monopole picking up charge.
Right. So the statement of this fundamental distinction is this Q is the charge that's picked up by a probe monopole.
Why does the probe have to be a monopole?
That's what I'm using.
But could that have been something else? Because you had something that annihilates with a partner.
Right.
But could it have been something other than a monopole?
So it depends on the phase. For the 2D quantum spin, the 2D topological insulator, I would use a pi flux instead of a monopole. It plays the same role. So in each case, so the more general question, which I perhaps, which I would have come to, but since you asked them, so given a system with some global symmetry, the more general thing you want to do is to couple that global symmetry to a background gauge field and ask about the response of the system to that background gauge field, right? And non-trivial physics of that background gauge field is in the gauge fluxes that you carry. Now, in the U1 case in 3 dimensions, you have magnetic monopoles. Okay. Now, an ordinary insulator has the monopoles have integer charge at Q equals 0. Now, in the topological band insulator, it's been known for a long time implicitly that the monopoles have charge E over 2. And for the students in the room, this is a good exercise to try and prove. The simplest proof of it, if you're a condensed matter type person, is to recognize, to argue this based on the known surface theory. So the surface, we have a single Dirac cone, right? Now you put your topological insulator on a sphere, right? And then on the surface, you have your Dirac equation on a sphere. Now imagine you have a magnetic monopole at the center of the sphere, and resolve the Dirac equation on the sphere, the two-dimensional Dirac equation on the sphere in the presence of this magnetic monopole. And then argue that the ground state has charge plus minus E over 2. Now how that comes about is that this Dirac equation will have 0 modes, 0 energy states, which there will be a pair of 0 energy states. Sorry, there will be a single 0 energy state, and occupying it and not occupying it will differ by integer charge. There's symmetry that interchanges these two, and so it must have fractional charge. So that's the most straightforward way to prove it. Now there's a fancier way for the field theorists. So you might know that the topological insulator has this theta equals pi electromagnetic response. As theta equals pi, by this thing known as the Witten effect, endows the monopoles with half integer, with electric charge that shifted from integer by a half. Okay, but what's the importance of the statement for our original question, right? Which is whether these topological band insulators are stable to interactions or not, right? So we see, so what the statement by us is that the probe magnetic monopole has fractional charge, right, which is quantized because of time reversal invariance. Okay? Now let me turn on any perturbation, including interactions of any strength whatsoever, right? I cannot change this fraction with this half continuously to 0, right, because it's quantized. So the quantization of the charge of the probe monopole guarantees that any perturbations, even if it's nonlinear interactions, however strong it is, cannot destroy the phase unless there's a bulk phase transition. Okay? So this is the kind of absolute stability argument that we were seeking, right? And it's, you know, it's not it cannot be a statement that you can understand within band theory, right? Because you're asking specifically about interactions. So it turns out that this way of characterizing the topological insulator is much more fundamental than the band theory way of characterizing it, right? So really, just like to characterize a superconductor, the most fundamental way is to say there's a Meissner effect, right? So what's the most fundamental characterization of a topological insulator, right? It's this guy, to say that the monopoles have charge half.
Sorry, just to understand, there's charge half sitting at the monopole and the remaining charge half at the boundary.
Absolutely, that's right. Or at some other monopole sitting somewhere else. Because the total charge inside the medium can't change, right?
And sorry, since you said this in field theoretic terms, then since you're saying this is the most fundamental way to characterize a topological insulator, then in field theoretic terms it is that you have a theta angle which is pi and
Yeah.
not 0.
That's right,
That
yeah.
is for all topological insulators, is that
No, for the standard topological insulator.
standard
Right.
band insulators, this is the way.
Exactly. There's not a complete characterization. There's one more thing. In field theoretic terms, there's also a gravitational analog that one has to specify, which corresponds to specifying in condensed matter terms the thermal Hall conductivity itself. But you know that can be taken care of. But there's at least a partial but completely non-perturbative characterization. Okay, from this point of view, let's ask what's the role of Fermi statistics and of the Kramer's degeneracy, which plays such a crucial role in the band theory description. Of course, band theory doesn't exist without fermions, and those of you who've heard, who are familiar with the band theory description of the topological insulator know the crucial role played by the Kramer's degeneracy of the electron at this high symmetry, at say k equals 0, high symmetry points. We're not doing band theory now. So from this point of view, if we're characterizing the topological insulator as something which has this fractional charge on a probe monopole, how should we understand the role of Fermi statistics and Kramer's, right? So let's take seriously this idea that if we in a topological insulator, the magnetic monopole has charge E over 2, and the time reverse partner also has charge E over 2. This means that if I bring these two things together, the resulting object has charge 1, and the resulting object, because it has charge 1 and net 0 magnetic charge, must be the same as the underlying electron. Right? So let's demand that M and Tm, when they bind together, behave like the underlying charge E object in the theory, and ask what the properties of this charge E object are. And so this is the next homework problem for graduate students, for PhD students. It's a really cool homework problem, particularly if there are experimental students in the room. I don't know about any of you. I periodically get the urge to do experiments. No one lets me into their lab. But theory is harmless, right? So if you're an experimentalist and who has the urge to do a little calculation every now and then, this is a fun calculation to do. And actually, I've been teaching quantum mechanics for first year PhD students for many years. I put this in a final exam, and amazingly enough, the students answered it correctly, mostly. Yes, so this is all advertisement for the problem, and then maybe I should stop, right? Yeah.
You could go on for a bit unless people have very pressing constraints.
I'm happy to go on for how much ever longer.
Whatever you folks think, but you can.
Yeah, but certainly I want to describe this homework problem for the students, because so what we want to do is to study this bound state of M and Tm inside this topological insulator, where M has charge half, Tm has charge half, and study their bound state and ask what the properties of that bound state are, right? So imagine there's some central potential, right? Take your favorite potential, which leads to the formation of a bound state. And so it's really solving a two-particle quantum mechanics problem, right? Now, the interesting thing is that M and Tm, they see each other as a charge sees a monopole. Okay? They differ from each other by, one. Convince yourself that M and Tm see each other as an electric charge sees a monopole. Okay? Which means that if you fix, say, Tm here and you take M and you take it around the loop, then there's a Berry phase, which is 1/2 of the solid angle subtended by the loop at the origin. Okay? Now, this fact is enough to show that if you solve this two-particle quantum mechanics problem, that the spectrum is two-fold degenerate, right? And furthermore, since time reversal interchanges these two objects, M and Tm, so the relative coordinate, any two-particle quantum mechanics problem, you fix the center of mass, and then it really becomes a single-particle problem, right? So the relative coordinate is odd under time reversal, right? So you have a particle moving on the surface of a sphere with a magnetic flux at the origin, and the relative and the coordinate of that particle is odd under time reversal, right? Now you solve that quantum mechanics problem, and you'll find that the ground state, first it transforms the spin half under the rotation group, and second, it's under time reversal, there's a Kramers degeneracy. Right, because it's the coordinate it's the vector that takes you from M to Tm. Exactly. Right? So this object is a Kramers doublet, and it transforms the spin half under spatial rotations, so which then suggests that it's a fermion. So if you make a spatial rotation, it has a spin half, picks up the right phase factors, and indeed this is a fermion. So we conclude that if somebody came and told you that they have a medium in which probe monopoles have charge half, then we know that if there's a unique kind of charge E particles in that medium, that those particles must be Kramers doublet fermions. Right? So it tells you, for instance, that bosons with charge E that form an insulator, if they cannot be in a phase where they have this theta equals pi response. Right? So I just showed that this charge half on the probe monopole is the same as having theta equals pi. Right? So theta equals pi, we just showed for a time reversal symmetric insulator is a property of an insulator of Cramer's doublet fermions. It cannot be an insulator, say, of bosons of charge E. Suppose some cold atoms person came up with a charge E boson, charge 1 boson insulator. And cold atoms people, they say they can do anything. So maybe they'll make a magnetic monopole that couples to that global U1. And they tell you that they have charge half. We can tell them that they cannot be preserving time reversal. So it's just not consistent.
Sorry, just being intensive. So your point is that if you had fermions in the system where, say, theta was pi,
Yeah.
then necessarily you'd have to have them in Cramer doublets. That is, they
No, there's 2 points. So the conceptual starting point is to say that theta is pi, or what's the same thing, that this monopole has charge half, and that I have charge U1 and time reversal, and a unique species of charge 1 particles, which are underlying charge 1 particles, right? So under these conditions, I ask, when can I have this theta equals pi response? When is it consistent, right? It's only consistent if the underlying particles were Cramer's doublet fermions.
Let me just say something. He's saying that he's assuming that this monopole anti-monopole bound state is the basic charge carrier of the system. But he's shown that the monopole anti-monopole bound state is a fermion. And
Exactly.
the basic charge carrier must be.
That's right. And furthermore is Cramer's doublet.
In other words, you could not have had, I mean, I'm just trying to understand, this bound state has this property that it's fermionic, etc.
Right.
And has spin half. But in addition, there can be bosonic states and so on. What?
Right. So the other assumption here is that there's a unique kind of charge carrier. There's that it's a system either. So I decide what my system is. Is it a system of bosons? Is it a system of fermions? You know.
Okay, I understand. So there is certainly this bound state.
Right.
And if that's the unique thing, then that's what.
Exactly. So this statement, let me say one thing just for the field theorists in the audience. This statement is also possible to prove without knowing any of this stuff on purely formal grounds. You have to ask, you know, you're talking about when is theta equals pi a consistent, when is theta equals pi in a U1 gauge theory consistent with time reversal invariance, right? If it's consistent in the theory of bosons, then you should be able to formulate that theory on a non-spin manifold and have that theta equals pi be time reversal invariant, and that's not possible because it's, what theta multiplies is instanton numbers quantized differently on non-spin manifolds compared to spin manifolds. And to show that it's Cramer's doublet requires the complicated thing of putting this U1 gauge theory on an unoriented manifold, and you can then show that it's only consistent with what's this known as the spin C plus structure, right? So you people, probably the field theorists know these things very well, right? So these field theoretic facts have very simple, concrete, you know, graduate student level interpretations here.
Theta is a term in the Lagrangian for the gauge field.
For the probe gauge field.
Yes.
That's right.
So what does it mean to say that this system has theta is equal to pi? It means that the electrons of your system minimally couple to your gauge field.
That's right.
Where the gauge field has a pi f wedge.
No. If you integrate out the dynamical electrons and you look at the response system, then you have theta equals pi. That's right.
Oh, I see. It's not as if the starting theory has a theta.
That's right. Yeah.
And because the thing is gapped, you're going to get a local Lagrangian.
Exactly. That's right. Yeah.
You do a long wavelength expansion.
Exactly. Yeah. I mean, the universal feature of the answer is where you take the gap to infinity. So then you have a purely topological response. Okay, so maybe this is the last thing I want to say. I'm happy to keep talking for much longer, but in terms of things that I wanted to say, perhaps I should go through this slide. And so if you followed it this far, then you can ask, suppose I gave you a medium time reversal invariant medium in which a probe monopole has charge E over 2, does that uniquely tell me that it's a topological band insulator? Meaning it's smoothly connected, it's a topological band insulator beefed up with some interactions. Or could it be an entirely new phase of matter, right? And the answer is that it's not necessary that it's just the standard topological band insulator. And in fact, we know that there's 4 distinct time reversal symmetric SPT insulators with spin orbit coupling, which all have this property that Q equals E over 2 on a probe monopole. Okay? So only one of them is the standard topological band insulator, and the others are missed by band theory, but they exist as topological insulators. Right? So this is in part answering the other question that I posed, whether there are other states, whether there are states of matter that exist in the presence of interactions as SPT phases, which are missed by the free fermion band theory, even for the standard.
So just to understand this, you mean one of these 4 can be connected by turning off interactions?
Exactly.
Topological band.
Right.
But not the others.
But not the others. That's right.
And just since you made this comment about the effective Lagrangian, all of them are characterized by the QED Lagrangian with theta equal to pi.
Yeah, but they differ. So no. Even there's a bulk difference. Okay, so
Is it RR dual?
yeah, so one of them, there are 2 of them have differences in the. So the standard topological insulator has both the F wedge F and the OR wedge R, but the other ones they have a different OR wedge R. So and for the 4th one, you see the difference only if you go to an unoriented manifold. The partition function on an unoriented manifold on RP4 is -1 instead of +1.
So there's some sign there.
There's some sign. The entire business, because of time reversal, from the point of view of partition functions, has to do with the sign of the partition function. But there's very simple physical characterizations of all these states.
And you see this characterization entirely in the bulk. You can
This monopole business, everything is a bulk characterization, right?
Now suppose you compute the partition function on a manifold with a bulk.
Yes.
Now what will you get?
Okay.
Sorry, just before please answer that, but just as you very beautifully explained the physics with the monopole, is there a similar way to also explain the difference between the 4 phases, these 4 different phases, by introducing other topological objects and not just monopoles in the bulk?
Since they have to do with responses to space-time, either gravitational or to changing the orientation, it's harder to do that. It's much easier to capture it in terms of the boundary, in terms that experimentalists will understand. And that's what was going to be the rest of this talk, to talk about experimental distinctions.
Continue the detailed discussion later.
Yeah, poor experimentalists.
Get to the punchline, we can judge.
No, so I'm happy to stop at any point now.
But I think
This might be a good place to stop, right? Yeah.
But we get to continue.
Yeah, I can answer your question specifically. So, yeah.
So I think we are trying to
Questions can be there subsequent. Okay. Right now, I think you've got invitation.
we'll probably get rid of this now. Oh, thank you.
Started just at the right level, so I could understand.
I don't need to be recorded now, right?
I think now.
No, it's just free for all. This.
What is that?
I don't need to be recorded anymore. Oops.
So I don't know, today the recording was possibly outside.
Not even sure how it turns off.
Later on we will have our own cable.
No, this is the BTP guys, no? This is what Rajdeep said. Next time onwards we'll have
You're meeting me at 2:30?
Yeah.
All right, okay.
At 4 o'clock,
Tamil way?
Yeah.
Yeah. All right, very good.
Thank you.
Okay, so if you don't have a boundary, right? So first let me argue that this is the answer. So what we care about is things. We don't care about the magnitude, where j is an integer. Right? I'll tell you exactly what this integer is. So the simplest way to, so this integer is the index of a Dirac operator on this 4-dimensional space-time manifold. And
Sorry, say that again. This integer is the index.
it's an index of a Dirac operator. And it's very easy to argue by taking a simple model for the topological insulator, which is just a massive Dirac phenomenon. Right? So we take Lagrangian, which is psi bar I d slash psi plus I m psi bar psi. Right? And let's imagine calculating the partition function as function of background gauge field and the background metric and this mass. Right? And divide it. You know, the partition function is itself not well defined. Right? It has orbit and we have to regularize. So let's look at the ratio of this guy to the same thing with minus the mass. Right? So that's a regularization if you wish. Right? Now, this thing is a product of, so this Dirac operator has some eigenvalues. Right? It's summation, so it has some eigenvalues. It's just identity. So it's lambda I plus I m divided by product of I and I minus I m. Okay? This Dirac operator is such that there's a gamma phi that anti-commutes with this, so the eigenvalues come in pairs. For each non-zero lambda I, there's a corresponding minus lambda I. So I can write this product, so this guy, is product lambda I bigger than 0 of minus of lambda I squared plus n squared divided by minus of lambda I squared plus n squared times a product over the 0 modes of the Dirac operator. Right? The 0 modes don't have to have partners. Right? So for the 0 modes, I have In times the number of, so the 0 modes have definite helicity, right? There's a positive helicity and negative helicity, right? So let me just count both of them, right? Divided by minus In, then plus n minus, right? So in this ratio, these two things cancel off each other. And the only thing that doesn't cancel is coming from this relative minus sign. So this guy simply becomes minus 1 to then plus n minus, which is the same as minus 1 to then plus minus n minus, which is the index of the Dirac operator. Right? So I erased my formula, but so the phase, so we don't know whether it's positive mass or negative mass that corresponds to the topological insulator. That depends on other things, right? But one of them, there's a difference between these two signs of the Dirac mass in the bulk, right? So minus 1 to the j is the topological part of the partition function that we care about, right? And it's plus minus 1, right? Now, then there's an index theorem that relates this to these f wedge f type things. I will get the normalization right, but I think
To some normalization.
it is 1 over 2 integral f over 2 pi x over 2 pi. And for this R wedge R, I can't get the normalization right. But I think in terms of sigma, the signature of the manifold is sigma over 8 or something like that. Yeah, they can check this, I think. Yeah. So this guy is the same as EDI pi over 2. Integral f over 2 pi wedge f over 2 pi minus sigma over 4, something like that. Okay. So this is the theta term at theta equals pi. That's without a boundary.
Yes.
Right? So now if there's a boundary,
So, sorry, can I just
Yeah.
Just to make sure, I mean, the way you're doing it now, you have an external electromagnetic field,
Right.
and you computed the Dirac operator in that background,
Right.
and J gets related to FHF of the
Exactly.
external,
Yeah. That's right.
The theta term you described earlier, that is, okay, yeah, that's the same thing. You integrate out this massive guy in
That's
the
right,
presence of
yeah.
Okay, go ahead. Sorry.
Right.
Yes, okay, okay.
So now, I mean, this is manifestly time reverse invariant because this is just a phase, right? It's not a complex number. But in the presence of boundary, and it's little, I mean, this index theorem tells you that this combination is an integer, right? Which is what makes this into, makes minus 1 to the j, makes this object plus minus 1.
But that's time reverse invariant because it's theta equals pi.
Because theta equals pi, that's right.
So it's not a phase. I mean, meaning it's 1 minus
It's 1 minus 1. But in the presence of a boundary, this thing is no longer quantized to be an integer.
Right.
Okay? So you have to add a correction term. And the correction term is precisely this eta invariant of the boundary Dirac fermion.
So is that essentially a Chern-Simons term?
It's morally a Chern-Simons term. I've been beaten into submitting that I should talk in terms of eta invariance and not.
I see. I don't know this actually. So you're saying, I'm sorry, so if you have a boundary, then
Yeah.
In the presence of this gauge field, there's an extra term which comes in.
Right, because this guy,
This of course.
let's forget this gravitational correction, right? Let's just take this guy.
Yes.
Now, the fact that this thing is quantized to be an integer is a property of a closed manifold. So when you have an open boundary, there's a problem. So, but then there's, from a purely math point of view, there's this, for manifolds, the boundary, this index theorem is replaced by the APS index theorem, which has an extra term at the boundary that corrects this guy. And the extra term is, it's called eta, and it can be defined in terms of the determinant of a Dirac operator in 2 plus 1 dimensions on the boundary. So from that point of view, that's how the surface Dirac cone shows up.
And this thing, a positive mass Dirac operator and a negative mass Dirac operator will have different.
That's
eta,
right. Yeah, that's right.
So the difference at least between positive mass and negative mass would be a Chern-Simons term.
That is right. At the boundary.
May be a
Yeah.
complicated thing.
Yeah.
The difference between eta and
Absolutely,
minus
that's
is bang on the nose. That's
Exactly, that's right. Yeah. So that's 1 over 4 pi ADA,
Yeah.
while the eta, the variation of eta, yeah, exactly, yeah,
Is that right? I see.
yeah.
That's why they don't
Uh,
want to call it.
Sorry?
That's why you don't want to call it a Chern-Simons term.
It's
Yeah.
like ABA, but not wrong. Right?
Wrong one there. The difference between them is right term, correctly one there.
Okay, I see. I see.
It's like integrating on a fundamental Dirac fermion gives you a shift of level half.
Right.
It's that.
It's that fact, that's right, yeah. So the eta invariant is a gauge invariant way of writing the determinant of this Dirac.
Dirac fermion gave K, doesn't K change by 1?
Half.
Fundamental fermion change.
So this is, so these facts are actually explained very clearly in this paper by Witten from 2015. It's a review in Reviews of Modern Physics.
Topological insulation?
Yeah, free fermion path integrals and topological phases, or that, something like that. I learned it from Witten.
No, one more question. You explained to us that these topological insulators have massless degrees of freedom on the boundary.
Right.
So,
No, that's only in the free fermion description.
oh, that's not true more generally?
So more generally, you can have gap boundaries
Oh, I see.
with topological order, with non-trivial TQFTs. But with, all you need is that there should be, you need the appropriate anomaly for the boundary theory. Whether the anomaly is realized by a gapless theory, or whether it's realized by a topological theory, that's non-universal.
No, that's what I was going to ask. The whole idea of getting this partition function without additional massless degrees of freedom. I mean, writing this down, including the boundary term, assumes that there are no massless boundaries.
No, 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 no. So this eta business. Okay. So let's briefly discuss the boundary theory. Right? So if I have in 2 plus 1D, I have the master's Dirac formula. Right. And I try to write down its partition function. Right. So I will write it down as some product of some eigenvalues lambda I. Right. But maybe I should use a different. Let me call it chi I. Right, to distinguish it from the bulk lambda i's. Right. But then I have to regularize this. Right. And let me regularize it by having another massive, I have one master's Dirac formula, then let me have a massive Dirac formula. Right. And then eventually I want to take this mass off to infinity or something. Right. So the massive Dirac formula will give me another chi I plus IM. This is a place of no return.
What do you mean?
Somewhere.
I have enough
Oh,
chalk.
you mean it's not going up and down?
No, the chalk keeps falling down.
Oh, I see.
It's a black hole. Now again, what we care about is the phase of the partition function.
Even though the partition function itself will be horribly non-local.
It will be horribly non-local, but we don't care about the magnitude of the partition function.
You mean because you have gapless excitations?
Yeah. So, if the only thing that's of interest to us is the phase, then we can ask what that phase is. So that's where the parity anomaly exists, right? It's in the phase of the partition function. And the phase here is simply related to the sign. I mean, if you take the limit of, so you can write this, take the modulus and write the phase.
Yes.
And the phase is, you can see, is precisely related to the sum of sine of chi I. Sum over I. But of course, this expression is meaningless. It's you have to regularize it.
Right.
And this mass gives you some particular
And the
regularization.
phase will depend on which sign of mass you choose, right?
The phase will depend on which sign of mass you choose. That's right. Yeah.
For the regulator.
Sorry?
Which sign of mass you choose for the regulator.
For the regulator, absolutely. Yeah. And you choose with different regulators, you'll get different
Okay.
choices. Yeah.
No, so sorry, so I sort of missed the thread here. Let me just back up a bit. So let's say you had a topological insulator and you put it in a, say it's a 3D material, you put it on a geometry with a boundary in an external gauge field.
Right.
You characterize the response in terms of whatever the effective field theory is, including a F term and a boundary term.
Right.
And then you look at the difference between the original system and say its time reversal, or at least taking n to minus n, which is not time reversal, which is chiasm flip or something.
Yeah, I mean, I did that in the bulk just to get the phase of the bulk partition function, just as a way to regularize the bulk partition function. Right.
So let's say, and you want to somehow calculate the phase, you can calculate it precisely enough. Then the claim is that this phase, besides having the FHF term, will have the Chern-Simons.
Right.
And that
No. So the FHF term is in the bulk, and then the Chern-Simons is in the boundary.
is in the boundary. And no, but I was just saying, and then both characterize the material of
That's
the
right.
phase. And then your 4 different phases we started with correspond to different choices of the boundary. I mean,
No. So
you need the R wedge R there.
exactly, yeah. So they differ. So some of them differ by this coefficient,
So some of them differ there.
and and the fourth one, you don't see the difference in terms of these responses, but you have to go to this unoriented manifold.
Go to that.
From the formal, in terms of the boundary theory, we can give a very simple.
I see. Okay.
There's Condensed matter ways of characterizing it, which are very precise, which are very simple, but it's harder to translate that directly into field theory. The field theoretic way of describing it has to. The only way you can describe it is through You know, so the real point is this. You want to, so let's step back from just these topological insulators, right? So you have some system with some global symmetry G, right? And you declare that it's, that you're interested in a gap phase of the system with no exotic anything. So on every closed manifold there's a unique ground state. Right. So, and the theory is topological because it's gapped. Right. Now, take the gap to infinity. Right. You're interested in purely topological things. So then the partition function, in the absence of any external gauge fields, is just trace e to the minus beta h, and there's a unique ground state, and so it's just 1. Right. So the partition function is 1 on every manifold. Now, when you include a background gauge field, you can ask what the partition function looks like. Right. So there will be some action. It's a purely classical action for these background gauge fields.
Which has a derivative expansion.
Which has a derivative expansion.
Yeah.
Exactly. But now, if some of your symmetries, a part of your symmetry group G is time reversal, how do you gauge time reversal? Right? It's anti-unitary. Right? Now, the only sensible way to gauge it is to put the theory on an unoriented manifold. Right? So that's where this, so conceptually it's not very hard to understand why unoriented manifolds are important. That's the equivalent of.
It's still it's two different things, no? I mean, unoriented and time reversal.
No. So in Euclidean, right? In
I see.
you know, parity, time reversal, it's all the same thing, and
Okay.
use
You
this
take it on a Euclidean manifold.
exactly, yeah.
I see. And then you study the response.
Yeah, so that's why.
So being on an unoriented manifold is the analog of turning on X-ray. It's like a background gauge.
It's background gauge field for time reversal, exactly. So that's why some anomalies you can only detect if you put the system on an unoriented manifold.
I see. Okay, that's. I see. But sorry, then just to go back to this point, you were also making. So how does one? So what is then the connection between between topological insulators and anomalies? I mean, is it that on the boundary theory? So as you say, you have a system with a symmetry G, and it's gapped. So on closed manifolds, all right, nothing very interesting.
Right.
And some background. Now we go to systems with boundaries.
Right.
And is it that, and presumably the point is that then you can sometimes get uncapped excitations on the boundary. Is that the general wider story?
If you're in high enough, I mean, you may get ungapped. You may. The statement is that the boundary theory must have a non-trivial realization of this global symmetry. Right?
And non-trivial means
It has this anomaly. It has this 't Hooft anomaly.
it has a true anomaly, which means, sorry, just to understand it in your language, it means something with a partition function. What is it?
Right. So the theory cannot really be does not really have a well-defined action of the symmetry at the boundary. To properly define the response of the system to a boundary, to a gauge field at the boundary, you have to extend the gauge field to the bulk, right? And then it's well defined. But if the gauge field lives just on the boundary, it's not gaugeable. The system is not gaugeable.
And is that precisely that the Chern-Simons term is half, basically?
In this example, it's precisely the statement that the Chern-Simons term is half. That's right.
So say that again. So yeah,
Say, roughly speaking, what you get at the boundary in this case, where you have theta equals pi in the bulk, is a Chern-Simons term with k equals half on the boundary. Roughly speaking. But that makes no sense. It's not context. So that means that Chern-Simons Lagrangian is not gauging anything. Okay? But the combined systems.
Bulk plus, if you extend the gauge field to the bulk, you don't extend the dynamical degrees of freedom to the bulk, just the background gauge field you extend to the bulk, then it's completely gauge invariant, it's completely well defined. And the symmetry is preserved. Right? And the answer depends on the extension to the bulk of the gauge field, but the dynamical degrees of freedom have not. changed.
So that is the more general story, I see.
Yeah.
That you take this material, you put it on a surface with a boundary, you integrate out all the gap stuff anyway, then you construct your effective Lagrangian or whatever, and in terms of the background gauge fields, the contributions from the boundaries themselves are not gauge invariant.
That's right, yeah.
You need the bulk.
You need the bulk.
Yes. And so it's not so much that you have boundary excitation which are gapless and so on.
Yeah,
may
so
or may not be the case.
that may not be, it's not guaranteed to be the case, but the boundary theory has some anomaly, which is cured by that.
And that's what you mean by Prof.
Exactly, yeah.
And now that this FYJF cures the non-gauge invariance of the k equals half, is that as the statement that FYJF is a total derivative and evaluates to another k equals half of the boundary?
That's what I thought.
That's the naive story. That's probably the essential part of the story.
Yeah.
But if you really want to be precise, at least I've been chastised by Witten into not saying that.
Oh, really? I see. I thought that's what you were saying. I see.
No, that's what everybody in our field used to say,
Yeah.
right? And then we've all
And what is the
been
precise version? Can you say it as precise?
right. So the precise version is this APS theorem. I understand the point that is being made. So the boundary theory, so the boundary, it's modulus or something, the boundary, times the plus minus depending on which regulator you chose, yield the I pi over 2 eta, where eta is this, eta is a proxy for level half.
Yes.
You know, this entire thing is the same as, roughly speaking, level half.
Yes.
Right? Now, this should be combined with the bulk partition function in the presence of this boundary.
Yes.
And so let me multiply this by z bulk. So neither of these separately is well defined
Yes.
or even real, but the combination, the product, is well defined and is real. Right? And this guy is precisely e to the I theta, where theta is equal to pi times integral f wedge f with the right coefficients minus sigma, also with the right coefficient. Right? So let me just put it as pi. Now this APS index theorem tells you that this entire combination is minus 1 to the j.
Yeah, but it must be some sophisticated thing on funny manifolds or something. Because at least roughly speaking,
No,
it's basically that you look at how FYJ transforms under gauge transformation.
right.
But it
right.
is basically the boundary terms. So
Exactly,
Like a
yeah.
science term.
I know that.
Yeah.
This is what we were saying in condensed matter
Yeah.
for many years, right? That this is good enough for us.
Yeah.
I guess.
But the more precise statement is in terms of all of these
But
things.
I mean, just to ask that, sorry, I don't know these eta invariants, so that under gauge transformations, presumably they transform
Exactly the same thing. The variation of eta is the same as the variation of the Chern-Simons term.
level.
So the variation of eta when you change these things is
That's
the same.
exactly what you're saying.
Yeah, that's it.
So the value is the eta invariant, but as far as gauge transformations are concerned,
Exactly, it's the same.
I see.
It is, once one understands it, it's nice. But I think, the field progress without understanding.
You may have missed subtle things.
Yeah, you may miss some subtle things, right?
You may even miss some things if you're not.
No, so this kind of understanding is also useful in these dualities to settle one final point about whether the free fermion theory was really dual to this gauged fermion theory, whether it was dual to that plus a gapped TQFT, which was the boundary of one of these other things. So Max Metlitsky settled that by doing this heroic calculation of the partition function of the pure U1 gauge theory in the bulk on an unoriented manifold and doing this duality on an unoriented manifold at theta equals pi. and checking which ones you go to. It's a really horrendous calculation. Right? But for that, it was this more precise point of view that he used, because he was doing that before Witten started chastising everybody else. So I guess he didn't need to be chastised, but the rest of us need.
I see. And then one last thing, we can even go for lunch and just discuss it then, which is, okay, so this, thanks, I understand now also how the word Prof anomaly is being used.
Yeah.
But, you know, sometimes in, at least say in QCD
Yeah.
and so on, field theory, Prof anomalies, for example, the flavor anomalies of QCD, are also used to argue something about the spectrum of the theory.
Right.
You know,
Right.
and there the anomalies pertain to some global symmetries, but because they exist, you know there must be poles which go down to zero energy, and you therefore argue that the full interacting theory has some massless spectrum and so on. Now, what I wanted to ask was that in a similar vein, is it sometimes the case that you have a topological insulator, you expose a phase, and you can also say something about the gapless excitations?
Yeah. There are a bunch of examples like that, where the symmetry preserving surface state is necessarily gapless because of this anomaly. Right? But I'm not sure it's exactly the same statement as the standard field theory statement about the two anomalies.
You're saying you can't mock up that anomaly by a topological field.
Exactly. You
can't.
Mock up that anomaly by a topological field.
Exactly.
By gap boundary topology.
So I can give you the simplest example of this phenomenon where we first encountered it.
That's exactly what I was asking.
Yeah. So the simplest example is if you have two Dirac cones instead of one. So there's a flavor, NF equals 2 QED3. So psi alpha bar with psi bar directly slash psi. Massless QED3. But here is a flavor index, and the sum from alpha equals 1 to 2. Right? So this, the flavor symmetry
How many
is
dimensions?
Sorry?
How many dimensions?
2 plus 1. Right. So the flavor is U2. Right? And then there's a U1 associated with, so there's U1 gauge field, it's QED3. Right? So there's a flux conservation, and there's a U1. Right? And there's various discrete symmetries which let me not worry about. Right? And this time reversal. Let me impose time reversal as well. Cross time reversal. Now, perturbatively, I can't gap out these fermions. If I add a mass, I break time reversal. Or I can add a psi bar psi mass that breaks time reversal. I can add a psi bar sigma psi mass that breaks in SU2. This flavor. It's a Popoli matrix. It's a flavor, it breaks the flavor SU2. It's a perturbatively, I can't gap it out. What about non-perturbative? It turns out that I can't do that either. And this theory has an anomaly, which precisely, this can only live at the boundary of 3 plus 1 DSPT. And that anomaly can be used to show that this, even non-perturbatively, you can't gap this theory out.
And that somehow uses the classification of topological field theories?
No, it doesn't need the classification of topological fields. It's no.
How do you know that you can't gap it out and get the same anomaly?
Right, it does use some results from the classification, but it's a very, very simple result. So what we know, so the point is that so if a gap boundary were possible, then there's some bunch of quasi-particles, 1, x, y, blah, 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 which, there's a 2 plus 1D CFT, they'll have some grading, fusion, some standard topological data, right? The first thing you have to understand is that this really is a theory of bosons, not a theory of fermions. Is that clear to you?
No, sorry, it's not clear.
Okay. So the fermions here are not gauge invariant, right? They're not local operators.
Yes.
So you can ask what are the local operators in this theory? And they are monopole operators. Okay? They are monopoles of this U1 gauge field. And those monopoles transform as a doublet under the SU2. So if I just had this fermion, the symmetry is not even SU2, it's SO3. Because the center of SU2 can be absorbed into U1. But the monopoles, they transform as fundamentals under the SU2. Right? And they are bosonic operators. So this really is the local operators in this theory are all bosons. There's no local operator that's a fermion. Right? And there are local operators,
So what about cyber-sonic?
but that's a bosonic operator.
Oh, I see, yeah.
Right. So this theory must have the form, this times things that you can build out of the local operators, which are spin-half bosons. Right? And because you have a local operator that's a spin-half boson, you can take all of these to be singlets under SU2. Because SU2 doesn't have any projective representations. Right? So these will all be either spin-half or integer spin. Now, if it's spin-half, you just bind it to the local operator to neutralize it and make it into a spin singlet. Right? That means that the non-trivial TQFT lives in the spin singlet sector of the theory. Okay. That means that any anomaly in the theory cannot involve the SU2 at all if this thing were possible. Right? If such a gap boundary were possible, whatever anomaly exists must be an anomaly purely of the U1 closed triangle version. And then you can argue that that's inconsistent. The anomaly of this theory involves SU2 in the fundamental way. So that's what it is. It's not a very complicated argument, but
So it's something like you have this extra flavor quantum number, and if you want to get all the anomalies to work out, the topological sector is neutral for the SU2.
exactly, yeah.
So it just can't be.
It just can't work out.
Okay, I see. But all right, so the bigger picture then is, sorry, just to understand this, the anomalies refer to gauge invariance, etc., under background fields, and your surfaces have to arise as surfaces of the bulk.
Right.
Because of the various quantizations and all. And sometimes that also implies masters.
Sometimes, yeah, that's right, yeah. Then, yeah.